as a note for people, we are going to record all the lectures, and what Santanu is going to do is he's going to upload it in YouTube and share it. So to get the best out of the lecture, what I suggest is that maybe Santanu has a different way, but at least I would suggest that don't take notes. Okay, just listen. Just sit back, listen. Just take like just bare
Yes.
minimum notes, scribble something for your reference, but just listen to it. And then if you say, oh, I didn't understand this, just go back and watch the video. Because if you start writing, then you'll just lose the flow. And since this is much more time, like other courses, usually we just kind of take a long time, interact and all that. These are like 1 hour 50 minutes. I mean 50-55 minutes. So we'll try to go a little faster pace. Okay, so same thing today. I'm going to go at a lot faster pace, just to kind of give you an idea on what VLSI is, because most of you said that this is the first time, you have no experience, which is exactly what this course is designed for, people who have no idea about it. And even if you have idea, like Prachita and Satabdi, they can still, I think, learn from it, because now it will be a little bit more complete. It has been done in bits and pieces before. So just sit back, take very few notes, but listen to it. And like as I said, I'm going to go like really fast, but today's lecture is not for you to understand every detail of it, but just kind of get a very like a 30,000 feet overview on what this field is, what goes on, and what different processes are, what design methodologies are, and so on. So that way, it looks like a lot of you are already motivated. This is kind of, this lecture is to take your motivation to the next level, that you after this you just never leave VLSI. Okay, all right, so so this is the cell phone. This is actually my brother's phone. I broke it. I think it's at least a 10-year-old cell phone. So if you, I think everyone knows Moore's law by now, number of transistors doubling in a unit area per year or two, I forget now. But anyways, so if you go by Moore's law, this whole thing now has shrunk to maybe a millimeter now, this entire cell phone. That's how incredible the integrations are happening. And so this is an older cell phone, but it pretty much has all the elements which you see in every phone, right? Like, so let's start with this on the left-hand side. Let me just switch on the laser here. So, so on the right side, you have, oh, actually, before I start, I just want to make sure, oh, 1 second. I think all of you are familiar with all these Zoom things, but once in a while, I'll ask you, like, can you all hear me? Just, there is a raise hand in your, if you're on your cell phone or desktop, can you just raise your hands so that I know everyone knows how to raise the hands? If you can hear me well. Okay. All right. It's about Soumya Kadagre, Soumya Panda, Sushri. Do you know how to raise the hand? So typically we'll ask you, can you hear us well? Are you done this and all that? So you don't have to do any texting or anything. You just raise your hand. So Susri, Soumya, if you don't know how to raise your hand, just go to the, I think it's on the, let me see on the phone where it is. Yeah, on the phone, you'd see on the bottom, there is like share, participation, more. If you go to the more, you should see a, thumbs up, raise hand. You can do that, okay? So now you guys can lower your hands. And same thing, if I say, do you guys understand it? You can just do a thumbs up, or if you didn't understand, you can do a thumbs down. Yeah, please don't feel scared or anything like that. I mean, this is supposed to be helping you understand all the concept. And sometimes if it is taking long, then we can take it offline. But there's something absolutely you can't understand, then definitely let us know. Okay. And also, if you have a question, you can raise your hand as well. So that way we know. So let me just switch to the participants here. Okay, and you can send questions on the chat window and all that. I think you guys all are experts in that now. Okay, so if you look at the cell phone, for example, if you look at this very end, the microphone, that's actually a VLSI chip, and I'll actually show you a a slide showing how those microphones look like. And then you have a power management chip, which is VLSI chip as well. So power management chip is basically, so you have only one power source in your cell phone, right? Your battery. But all these chips actually require different types of voltages, different types of currents, and so on. So that's what this chip does. Then you have the memory, which obviously, you know, nowadays in your phone, you have 4 gig memories, 8 gig and so on, and at least 1 or 2 gigs. So that's the memory, the RAM. And the heart of this cell phone is your processor. Obviously, this was like said 10 years ago. Now it's a, you know, 2 gigahertz, 8 core Snapdragons and so on. There's obviously a speaker, but speaker is actually, believe it or not, is actually a VLSI MEMS device as well. So this microphone is a MEMS device, the speaker is a MEMS device, and obviously the earphone, proximity sensor, the imager is actually a VLSI chip as well. That's your film. I mean the camera. Then the Wi-Fi Bluetooth, that's the one which communicates with your router or Bluetooth device. So that whole radio chip. So there is a radio chip here with a baseband chip which converts your digital encrypted thing back into voice or whatever data. So that's also a bunch of chips for that. The GSM, GPRS, GPS, that's the heart of the chip, which is the radio. Actually, that's the radio here. This is the baseband chip, which does all the processing. So converting your voice into digital, your data to digital, sending to the cell phone tower, getting it back, de-encrypting it, demodulating it, and so on. All that is actually done by here. And there's a power amplifier which sends watts of data into to the cell phone tower. So you break down any consumer system. You know, you break down your PC, you break down your, you know, washing machine, your TV, and they're all a bunch of chips like this performing like this. So everything is a VLSI chip. Okay. So someday when we meet in office, I'll actually give you the physical device. Okay, so the VLSI, obviously everyone knows, very large scale integration. So what's integrated? Well, a lot is integrated. And like I say, Moore's law, you know, almost twice is getting integrated every year or two. So a lot of it is getting integrated. For example, in this cell phone, that radio chip, which I showed you, you know, 30, 40 years ago, that would be this, or even 20 years ago, that would be your entire radio chip, actually much more. So this is actually FM radio I'm showing on the right, and that's compressed into a chip. This processor, you know, 10 years ago, your giant desktop, that's actually much more powerful than that. It's powerful than an entire room of computers which you had in 1980s. That's how powerful these devices are. The cameras are unbelievable because, you know, I've been doing photography for what, 30 years now. So I used to use these SLRs before. And the quality is just amazing. The same chip now does more than what your SLR used to do before. So you have this giant camera, mechanical camera, which is, you know, crammed into this VLSI. Then, you know, gyroscopes. So, you know, you have your phone, when you rotate it, the screen rotates. And also you don't realize that when you're doing navigation, if you lose your GPS signal, that's what does your local navigation as well. So that's actually a chip. And actually I've been consulting with Panasonic now. They used to be a small startup almost for 7 years now. And that's what we've been developing, a gyroscope, MEMS gyroscope with a CMOS chip to it. Okay. So I'll show you a couple of systems, you know, VLSI system, how they look. So this is a typical microphone. So the microphone you have in your cell phone, if you break it open, that's actually a VLSI chip plus a MEMS microphone, which is also a VLSI, but it's a mechanical system. So what it is, it's actually 2 plates of capacitors with air in between. So when you speak, you actually compress this plate here, it changes the capacitance, and then you have the circuitry which you know, converts that change of capacitor into electrical signal, which, so it's voice to capacitance to electrical signal, basically is how this thing works. So this is by a company called Knowles, and most of the cell phone you have right now probably has this chip here. And you can see here, the entire microphone here measures only 1.6 by 1.2 millimeter by 2 millimeter, roughly, like size of a rice grain. I mean, it's kind of amazing. And the chip is even smaller, right? So this whole thing sits in a cavity and in your phone for your microphone. This is another type of, this is a newer microphone called Piezoelectric. Instead of capacitor, it's actually a piezoelectric microphone. So you can see there's a piezoelectric here. which gives you voltage as pressure is applied, and that pressure is your sound pressure. And then there's the IC chip here. This is actually by a company called Vesper, and I designed the LNA is designed by me here, somewhere here in this, there is a LNA. So I consulted for them to design a LNA. And this is now in all the Amazon devices, the Echoes and all those devices, they have these microphones now. Very small, very sensitive, and very low power, the piezoelectric one. So it was started by a professor from U Michigan, actually. And that's how, if you look at the entire microphone, that's how it looks like. So the MEMS microphone sits with a opening here. So your sound, when you start speaking, that changes the air pressure, which changes the kind of vibrates this piezoelectric, which generates a voltage. And then you have this VLSI chip, which converts that voltage into electrical current or whatever it is, and digitize it and send it to the processor. And, and that converts into all the signals you need. MEMS accelerometer, you probably don't realize it. You're probably using them in so many things, obviously robotics. Nowadays in cars, like for example, the airbag deployment is done by accelerometer. So accelerometer is basically, like it says, it detects acceleration, change in acceleration, even your cell phone. So like, when you do shake, or you're playing a video game, or you're even rotating and all that, that actually in conjunction with a gyroscope, accelerometer, that senses that and sends all the signals. Obviously, military applications, other consumer applications like navigation and so on. And this is a typical accelerometer. The company I consult for the gyroscope, they actually make the accelerometer as well, a different kind of accelerometer, but kind of similar. So this is actually a MEMS device. As you can see, it's actually a mechanical system, very small. This is also a size of a grain, a rice grain. And you have all these little capacitor plates. So when you start accelerating in one direction, what happens is, because you have a mass, and the mass has a force because of the acceleration, because it looks like this mass spring, it starts moving in one direction, and that changes the capacitance, and basically measure again the capacitance and measure the acceleration. So a typical sensing circuit is like this, where you have an op amp in feedback with some resistor, and this capacitor is actually the capacitor in your accelerometer. So when your car is accelerating, or like, when you go and crash your car, it will deaccelerate so fast that it actually changes that change of capacitance here. That gets converted to a voltage, sends it to the computer. The computer deploys the airbags, and so everything happens within less than a millisecond. And you basically, the airbag comes on before you smash into the steering wheel of the vehicle. So that's one of the big applications. Same thing, the angular velocity I was talking about. So this is one chip, a different kind of gyroscope, but similar principle. So like I said, I've been designing circuits for sensing this angular for 7 years now for this company, which is Panasonic now. So the idea is to sense angular rotation. So like, for example, you take your cell phone, and when you rotate it, and that angular rotation gets converted to what's called a Coriolis force. That's classic physical Coriolis force. And so essentially, it's a small mass system. Again, this is size of usually 2 millimeter or 3 millimeter by 3 millimeter, something like that, very, very small. So when you rotate, what happens is, again, the same thing. These mass spring systems are actually vibrating at a certain frequency, and that vibrating frequency starts changing in amplitude, which is proportional to your angular velocity. And this is showing a finite element simulation method to simulate, when you're doing angular rotation, how the separation between the mass changes. That changes the capacitance, and that changes the amplitude of your oscillation, and so on. And again, you use a circuitry, some sort of so this is like a RF modulated demodulation system, where you actually drive this MEMS system, which oscillates at a certain frequency. And then when you add angular momentum, that oscillation frequency changes in the amplitude. You demodulate that amplitude, and that amplitude is directly proportional to your angular velocity. That you feed it again to the processor, and that senses it is okay, you've rotated the phone, or the car has rotated, or whatever it is, and then you do whatever actuation you want to do depending on your system. Okay, same thing. So CMOS imager, the imager you're sensing they are very, very complex now, the CMOS imager. but essentially that boils down to each pixel is nothing but a reverse bias diode actually. So, on a chip, you're creating these tiny dots of diode structures like this, which are, few micrometer by few micrometer. And, if you remember your device physics, it's like if you shine the light, and the light usually has a energy, which is Planck constant time the wavelength. If that light is greater than the band gap, then there will be a current flowing through it because it will take the electrons into the conduction band and so on and so forth, right? Or in other words, light shines on it, you get current through it, and that's it. So you detect that current, but obviously there are a lot of problems, issues with like noise and, black current and so on. So there's a lot of complex circuitry which goes into doing CMOS imaging, but that's essentially so it's a huge array of, like, you have 4 megapixel cameras, so you have basically 4 million of these sitting in like few, 10 millimeter by 10 millimeter or 5 millimeter by 5 millimeter chip. And a lens basically focuses that image onto the chip, and then all the circuitry which you design as a VLSI designer um, detects that image and converts it into all those beautiful images which you have been taking. Okay. Okay, so what I'll do is so how does this happen, right? I'll quickly walk you through IC design process. This is a very simplified process which you typically use in analog design, and I'll show you a digital design one later on as well. So typically what happens is in a smaller company, this will differ from people you ask, like people who are working in Intel have no idea. They're just given a small block and they design their entire life. But if you're in a smaller company, you're part of the entire chain actually. So typically the marketing guys will come and they give you a spec. So for example, they want to design an op-amp, they'll come and say, okay, we found a market for this op-amp. If you design it with these specs, then we can sell a ton of it, make a ton of money, and then we'll be all rich. Typically never happens, but that's the promise they start with. So as a designer, you take that specification and you come up with an architecture. Architecture means you are not putting any transistors yet or anything. You're just doing mostly hand calculations or high-level simulations, like using MATLAB or Simulink or Python or whatever it is, or in digital systems, you're just writing it in Verilog, basically. So that's your architecture. You say, okay, let me see what kind of architecture I can use. For example, this is architecture of a radio chip, a GSM cell phone chip. So given the specs, you come up with this architecture, and once you're happy with the architecture, you go to the next step. If you're not happy, then you go back to the marketing guy and say, hey, these specs are impossible to meet. It'll cost us too much. We'll not make money. You got to relax some of these areas. So he might come back and say, okay, we can relax here and so forth. And so this loop goes on for a little time. And then once you're happy with the architecture, you do the circuit design. So where you start designing each of the circuits, and that's where you choose what's called in VLSI the technology. So it's not, in VLSI, it's not like board level design where you go and buy components off the shelf or from the thing, and you didn't like this transistor, you replace with a transistor and so on. You choose a technology, and for that technology, everything is fixed. The transistors are fixed, the resistors are fixed, the capacitors are fixed. If there are inductors, they are fixed. So you have a very small set of components to work with to design this system. So that's why it's very, very critical to come up with the right technology. So what I mean by right technology is, like your cell phone, the chip is actually what's called they're using 7 nanometer devices, which is like essentially 2 oxide atoms. I mean, they're so small, right? Whereas your MEMS microphone probably is 180 nanometer because that's more suitable for that design because it's analog, low noise design. So you have to choose that right technology. Do I go for 180 nanometer TSMC? Do I go for 7 nanometer global foundries, or so and so forth? This is where you choose. And if you make a mistake, and you might spend 5 years and come back and say, okay, that'll be very costly. And the same thing with the circuit design as well. If you are having trouble with circuit design, then you go back to the architecture again and see if you can change something in the architecture to relieve you from circuit. If you can, then you go back to specification again and so forth. So it's kind of a loop. And then once you are happy with the circuit design and simulated it and all that, you go to the next phase, which is called the layout. And the layout is essentially converting this abstraction into physical drawings, which are given to the foundry to fabricate your devices, okay? And those are fixed design rule based on whatever technology you've chosen. And then you basically send these drawings, essentially a lot of polygons, and I'll show you what these polygons do in the next few slides. And you send it to the fabrication house, and they take these things, what's called wafers. They do a lot of khichdi on it, and then magically chips come out, and you package them and you put them on the cell phone, test it, and so on and so forth. Okay. Okay, now how do you go from this to a real chip, which goes into this package, which you put it on the PCB? So you have an idea, because this circuit is nothing but an abstraction. You could as well have smiley face here with 3 terminals. It doesn't matter, right? Just a model of what the reality is. It's not the real thing. So how do you go from here to here? So before I go to the next slide, any questions on so far, like something which just absolutely doesn't make sense, or you guys are with me? Okay, so any questions so far? Okay, good.
Yes.
Sorry, was there a question? Okay, looks like no. Okay, you guys are good. So looks like there is people are putting question marks. Yeah, that's a good one. And we were I wasn't using that. Okay, so I'll show you now. How do we go from here to here? So so essentially so this is a simple inverter. I think most of you by now probably recognize it. Essentially, it's a NMOS device, PMOS device, basically 2 complementary switches. So you either make it 1 or 0. So you either connect it to VDD or connect it to ground. So representing a 1 and 0. It's a digital inverter, but you have to represent it with physical device. So this is how you would connect them in your SPICE simulator or software, whatever you're using to draw it, and then connect it and simulate it and so on. But in reality, this is how it looks in the IC. Okay, this is a cross section of your chip actually. So if you cut your chip right in the middle of those inverters, and you just show, so it's like you have a cake, you cut the cake and you're looking at the layers of the cake, right? So this is like the side view of the if you cut the cake and you're looking from the side, that's how it looks like. So for example, this NMOS has a source area, drain area, some oxide, a gate here. There's some metal connection going from the NMOS to the PMOS, which is sitting on an N well, some source and drain, gates, and so on. You connect one level of metal, then you connect another level of metal, and between metals, there is all this oxide, which is basically glass, which is an insulator, so that you don't short all these 2 metal layers, because it's kind of a 3D stack of metal. So it's like a PCB where you're using different layers, and you have FR4 board in between the metal layers so that they don't short. Here, instead of FR4, you have silicon dioxide, basically. Okay, so what you do is, after you simulate, what you do is you generate what's called a layout. So this is what's the layout. So you actually draw a bunch of polygons. So let's say we're going to work on 500 nanometer design, technology for your lab here. So this should be like 500 nanometer, and this should be like 1 micrometer width, and these would be about 500 nanometer. So these are the lengths of different layers, and I'll show you what the different layers do in the next slide. You draw these, okay? And these actually represent each of these devices. For example, this is representing your NMOS. These 2 connections, metal connections, are basically representing this short here. And this VDD connection is here from metal 1 to metal 2 and so on. So you draw this and send it to the Foundry house. Now, what does the Foundry house do? So the Foundry house will get a layout. So let's say you just drew an inverter. So you would have drawn something similar to this. I have drawn the gate connection and so on. This is just for, kind of give you an idea. So this is like the top view. So you're looking at the top of the cake now, basically. And if you slice the cake here and look at the slide, that's how is going to look. So this is your cross-section view. So this NMOS, you can see it's an NMOS with a source drawn area. This is your gate, which is this gate separated by a thin oxide, which is an insulator, because this is a MOS transistor. And then you have this, what's called via, which is connecting to the metal 1, and so on. Now, how does it go from here to here? So what you do is you first start with the base silicon, which is called the wafer, and typically they're about 1 millimeter thick, sawed down to sometimes 0.5 millimeter, 500 micron, or sometimes for some chips it has to be even thinner for noise coupling reasons and so on. So you start with this base material. So I'm showing you the cross section now, okay? And you send this layout to the foundry house. So the foundry house, what it does is it takes this layout and it takes layer by layer, okay? And creates what's called mask and use photolithographic techniques. And, Santanu will be covering in detail when he covers fabrication process, how does this lithographic processes happen. And they take each of these. So for example, they'll take these two drawings, which are what's called the P well and the N well. This is called the STI process. They'll take these two mass and take the wafer and create these structures. So there will be a oxide, what's called a shallow trench isolation STI. They'll create a P well, they'll create an N well separated by this oxide so that these two devices don't touch, okay? So they take this drawing from, so if I show you a previous drawing again, they just take this mask and this mask and create these structures, okay? Using photolithographic techniques, which will be covered in a lot of detail in your fabrication. And then they take the next layer, which is your gate layer, defined in this green, and they'll create the thin oxide, then the gate layer, which is usually done in polysilicon, and then take the next layer, which is called the diffusion, and then they'll create the source drain areas using the same photolithographic technique. Then they'll take the vias which you have drawn and they'll put oxide so that it doesn't short, and they'll add this vias which are in older technologies are tungsten, now they're copper. They'll fill these plugs. So basically you have these 3D plugs which are connecting from your source drain area to the next level, which is metal. Next, they'll take the metal layer and again use photolithographic techniques to lay the metal. Now you have the connection. So you have the two drains connecting here, the source connecting to this metal, source connecting to this metal. And you have another layer of metal. They'll put another layer of oxide on top of it, and they'll add the vias and they'll put the second layer of metal. Let's say this is called metal 2. And that's how, so it's a step-by-step process. It's a planar process. So all the source and drain of all the millions or billions of transistors in that wafer is done at once. All the vias of those millions and billions of transistors are done once. All the metal ones are done once. So this is not like, it's your hand drawing. You're drawing the metal, then connecting it, then second metal, and so on. Because this is a planar process, every layer is done one at a time. Because once this layer is over, that's it. You cannot come back and do anything with metal one. So that's why all the metal ones are done at once. Okay. So that's it. So this is the fabrication. So in the lab or in your course, you're going to design this circuit, send this mask to the fabrication house, XFAB, TSMC, or whatever it is. And they take these 8-inch or 6-inch, what's called wafers. They are basically silicon disc, nicely cut, thin silicon disc. They take a lot of chemical and, essentially they do the khichdi here. It's literally cooking it. And out comes this wafer with lots and lots of chips, depending on how big is your chip. Then they cut it, slice it, and package it, and that's it. Your IC is ready for it to be put in the device. Okay, so that's showing how physical devices. Now I'm going to quickly show you. So I said the design process I showed you, that was design flow, which is the primary market here in India. It looks pretty much similar, but a lot of it is automated. You don't do custom design. In analog design, which is what I do most, me and Santanu we do, pretty much everything is custom. Okay, because the tools, they just it's a problem which tools cannot solve. The constraints are too much, and it's an unbounded problem basically for most design. So you're pretty much always doing everything in it. Digital, fortunately, a lot of it is just automation. So same process. So you start with the idea. So somebody gave you the specification. For example, somebody asked you to design a SPI controller. You start with this, and you start first with your architecture with what's called RTL design. It's register transfer logic in Verilog. So this is, for example, a simple Verilog code where it's a flip-flop and a mux. And then you do a verification where you simulate it using your simulation tool. If it is not meeting simulation, you go back in your RTL design. And this is probably one of a big job areas in India right now, the verification part. And these two steps are usually called front-end design. Okay, so it's a very simplified process. Actually, there are, Satabdi and Prachita now know when they did the professional course, this was a long series of like 12 steps. So I'm just showing you very like an overview of what they are. So typically once you've done this, what you do is called synthesis, because this code is a bunch of lines of codes. There's nothing real in this code. There's no voltages, there's no currents here. So what you do is you basically synthesize, and the tools, somebody has so they have another class now. Okay, so we have 5 minutes. So let me see. So maybe we can skip this. Yeah, so this one we have to be, so it's the same process. Let me see what I have next. Okay, so maybe I can just go. So yeah, so just 2 minutes here. Yeah, so you go through the same step, you go through the design, you do what is called synthesis, and then you do what's called gate level synthesis, you do the layout, you send it for fabrication, and same steps. And this is the last slide I wanted you guys to show that, from a job perspective, where most of the jobs are, they're usually in these 4 steps. So the RTL and the verification is probably, so the verification is probably in the number 2, but somebody will say it's number 1. Physical design is the part where people do the synthesis, what's called place and route, timing analysis, and these are the stuff which we did it during our professional course. And these are the main job areas, and especially if you're going in the physical design area, your CMOS knowledge has to be really good, and your digital as well as your circuit as well. Okay, and for RTL and verification, typically they want your, sort of your Verilog and digital to be much better. Okay, so I think I'll stop here, and maybe what we can do, Santanu, since they have a class, we can talk about the labs and all that in tomorrow's class. Okay, once you finish tomorrow's class. So every day they have a class after, so Monday, Tuesday, Wednesday, you have classes after this? Let me see. Everyone has a class?
Yes, sir.
Okay.
I think Monday,
Hello?
Tuesday, and Wednesday there is no class, I think.
Okay, so that's fine. I think we'll just make sure we
I
finish.
think Tuesday.
Yeah, looks like they have, right? That's what Sadhati said, that they have a class.
Yes.
All right, so we'll finish it here. What we'll do is we're going to have a lab session, maybe Friday or Saturday. We'll do that, so we can use that time to do any extra doubt clearing or anything like that. Okay, so these, I guess, because you have a class, we'll try to finish it. Okay, so looks like it's already over time. So okay, thank you guys. And if you have any questions, like I just said, you can send it on the WhatsApp group, or we'll discuss during one of the tutorial or the lab classes, or we can start with tomorrow's class. Okay. All right. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, sir. Thank you,
Thank you,
sir.
sir.
Thank
Yeah.
you.
Thank you.
Thank you.
Thank you.
Thank you, sir.